morning, everyone. I hope you're continuing to do well. We're going to continue on in our energetics chapter. Today, we're going to learn the lesson on bond enthalpy. This is going to be our second way of finding the delta H of reaction. We call the delta H here the change in enthalpy. And if it ever confuses you here, enthalpy, if you remember here, we're specifically looking at the heat energy. Because the universe is way too big a place to study, we're focusing on the heat energy inside your system. For us in chemistry here, the system will generally be just the particles that perform the reaction. So in this case here, your system is just going to be your chemical reaction. We have been saying here we can plot this on an energy level diagram. We've been plotting it. I have an enthalpy against sort of the reaction axis. We would start off with reactants and we become products. Although it's impossible for you to figure out what's your actual starting number or what's your ending number, let's say. Fortunately for us, we're just interested in over the course of the reaction, as reactants become products, do I end up gaining energy? Do I end up with the delta H as positive and endothermic? Or do I have one that's negative, which is exothermic? We're going to learn in total 7 different ways of finding the delta H. Yesterday we did a lesson on calorimetry. It was more an experimental method. You do an experiment based on the temperature change that your thermometer says. We were able to back calculate for delta H. This one here becomes our second way of finding the delta H here. We're specifically looking at bonds. Basically, whenever things are bond together, there's a certain amount of stored energy, and we're looking at trying to compare the stored energy in different bonds to try to get a sense on what this delta H is. We'll be looking at 2 pages on the data booklet, so make sure you have that handy. Eventually, we'll look at table 10 and table 11. Right? So, without further ado here, let's take a look at bond enthalpy. That'll be the start of our lesson. So this is going to be method number 2, bond enthalpy. We're going to start off just with a general comment here. Breaking bonds. Anytime you want to come in and you want to rip two species apart here, breaking bonds always requires energy. So I need to put in energy. You should be able to tell me that then therefore means endothermic. It needs to be absorbing this energy. And sort of in contrast here, forming bonds. Whenever we make new bonds, whenever we store energy between particles here, forming bonds tends to release energy. Right? It tends to put us in a more stable state, and then whatever energy that we don't need just gets released off. So this is going to be an exothermic reaction. So these 2 statements always happen. Anytime you want to break bonds, you put in energy. Anytime you form bonds, we release off any extra energy. So let's start off with a simple enthalpy level diagram. You could even say potential energy because that also measures the stored energy in the system against your reaction coordinate. Let's take a look at a very simple compound like hydrogen. So hydrogen, when it's elemental, we know it's diatomic, so HH. We will need to do a little bit of Lewis structures in this lesson as well, so make sure you're comfortable with that here. I'm going to plot out for you, so H2 is my reactant right now, and again, because there's way too many particles and there's too many ways energy can be stored, I may not necessarily know exactly how much energy we begin with. However, when I look at this HH molecule, I'm going to think here, these 2 electrons having negative charge, there's a certain amount of stored energy for these 2 electrons being stabilized by the 2 protons on each neighbor. So in that case there, that's just the amount of stored energy. That's called the bond enthalpy of HH. When I then apply the bond enthalpy, when I then come in and forcefully rip apart this bond, I need to endothermically put in energy. So this energy can be in the form of light, heat, whatever form. By putting in energy, I can rip this bond apart. I can artificially separate these 2 here, just for argument's sake here. Let's say we separate them completely in 2, so we end up with 2 H radicals. In chapter 4, we called that homolytic fission. We knew 2 electrons make up a bond. Let's imagine ripping it up evenly so that 1 electron goes to each neighbor. We already said having this unpaired electrons, we know these are called radicals. We know that's going to be unstable. On an energy level diagram, I'd expect these particles here to be a lot higher in energy. And that's exactly what happens here. It was happy, just stabilized the way it is. When I put in energy, eventually these H radicals here have much higher energy. Remember, we want less energy to be more stable. So this amount of energy that I put in is the energy we're going to be calling a bond enthalpy very shortly. But that's the amount of energy that I need to actually rip apart these 2 bonds. It puts us in a less stable state because I have higher energy. These guys here won't stay for this very long. They're going to try to pair up this electron any way they know how. They're just going to collide with each other here. This is going to be a termination step in your organic chapter next year. But basically, these two here, they could recombine. You can imagine having two of these H radicals. As they speed towards each other, they can end up relaxing. They can end up reforming the HH double bond. HH single bond. So in this case here, once they form that bond, again, they can relax a little bit here. They're not impaired. They have a full octet. Everyone's happy. They're going to end up reverting down back to the energy reading that they had before. And in that case there, based on conservation of energy, the quantity of energy is always conserved. So whatever energy I put in, once that bond then forms, it's going to radiate off any extra energy. Again, it can be in many different forms. We saw in chapter 2, I had excited electrons with electricity, and when it came out as light energy. Energy can come in multiple different forms. So that's just a sort of general overview of breaking bonds and forming bonds. And the kicker for this lesson here is, depending on who's actually making the bond, which elements, depending on what type of bond they are, single bonds, double bonds, the idea, different bonds store different amounts of energy. So the big idea here, before we get into some of the details, is this notion here. Because usually over the course of a chemical reaction, we're talking about some bonds breaking and some bonds forming, because the bonds themselves between different combinations are going to be varied, I can just compare here. If I have a bunch of reactants and I have a bunch of products here, I can sort of compare how much energy is used to break bonds. That's going to be an input in energy. That's going to be endothermic. That's going to be the heat term on the right-hand side. And if I compare, by the time we form products, we inevitably would have created new bonds. We would have ended up getting some energy released as the species can relax a little bit here. Energy released, as I'm going to mention here, these are new bonds, right? The bonds have changed as new bonds formed. It shouldn't be that surprising for you, just sort of generically speaking here. Well, if I put in, let's say, $100 and I get $20 out, well, in total, I put in more energy. Or maybe I only put in $50 to rip apart bonds and I get $2,000 out. Well, then I have a net release of energy. So again, I'm still not tackling the problem. I still have no clue what my starting energy or my ending energy is. Those are impossible to find. Those are called absolute enthalpies. But we can figure out, just sort of relatively speaking, how much did you put in, how much did I get out, to get a relative change in enthalpy. So that's the idea to carry on through this lesson here, although there's a few little technical notes we're going to get into right now. So I'm going to introduce to you our main term for today here. We're going to call these ones here average bond enthalpies. So average bond enthalpies. These ones here will be found on table number 11. We'll look to it in just a second here. Lots of definitions in this chapter, but fortunately most of the definitions have the same structure. So there's a couple things you want to mention here. So the average bond enthalpy is the energy that's needed to break. So between the two directions, I could have put in energy or I could have released energy here. I'm just going to look at breaking bonds. So the bond is already there. How much energy do you need to input to forcefully rip these two things apart? We're going to see in a lot of our definitions in this chapter here, there's always this pesky little 1 mole that comes in the definition. We'll see the importance of this later on this lesson. Energy needed to break 1 mole. So there's always going to be a pesky little 1 mole. In this case here, we're looking at trying to break bonds. They could be single, they could be double, triple, it could be any combinations. However, on our table, everything's tabulated for when they were in the gaseous state. So that's going to be one limitation of doing this bond enthalpy method here. Anytime you have a reaction that suddenly has a solid or a liquid, not that we couldn't do this method, it's just we don't have the numbers that we need. So 1 mole of that bond in the gaseous state, and the whole notion here of being averaged, it's being averaged over a bunch of what I'm going to call similar compounds. So gaseous state, it is averaged over similar compounds. So they could just simply ask you here, define bond enthalpy, and I'm just going to put BE for bond enthalpy. So I'm going to show you the table in just a second here. Let's take a look at, so we're looking at bond by bond. So if I look on the table and I look up the bond enthalpy, usually in brackets I try to define for you which bond I'm looking at. Let's take argument's sake here, let's take a look at a CH single bond. So you notice that this may be part of a much larger molecule. Maybe my molecule is plain old methane. We did that in our little organic intro. So methane actually has 4 of these bonds. When I do bond enthalpy, I'm looking at the energy I'm needing to input so that I can forcefully rip apart each bond individually. So I can focus on one of these bonds here and I can say, well, how strong is this one bond here? How much energy am I trying to put in so that I can rip these two apart? The table will tell me here, 414, it's going to be in units kilojoules per mole. Because in the definition we had this pesky little 1 mole, we know we are coming in and only ripping one out of the 4 CH bonds, but not just for one single molecule. I'm going to line up a whole Avogadro number, these ones here. I'm going to forcefully rip this apart. When I forcefully rip this apart, what's going to end up happening is the methane would still have 3 CH, it's still going to be CH3 with the radical, and just that one single bond is going to be ripped apart. So the energy change that I'm saying is required for this. Because we are breaking, we expect these to be endothermic, and in fact, all bond enthalpies are going to be positive delta H's. It's quota per mole, and what we've done is we just basically rip that apart. So I go CH4, and we end up with CH3 and an H. To emphasize that these ones here are radicals, usually we put that just a single dot there. It's homolytic fission, it's evenly split. Now you're going to say to me here, well, this is not the normal way this shows up, right? When hydrogen's by itself, it's usually H2. If I ask you, this is a nice multiple choice question. Which reaction here, let's compare two reactions. The one I just wrote, that's the correct one. If I compare it to, I don't know, it's a little bit harder to do. Let's do something like that, okay? Which of these reactions here is closest to the bond enthalpy? If I could just find the delta H of these reactions as written, which one would be equivalent to me doing bond enthalpy? When I bond enthalpy, all I've done is I basically ripped apart C and H. When I rip apart C and H, sure, I end up with two radicals here, they're super unstable. This one here actually corresponds to the bond enthalpy. Now, to be sure, the hydrogen here very shortly, it's going to run into another hydrogen here, it's going to collide together, they're going to end up forming H2 fine, but in that case there may also be some extra energy change there. So therefore, if I wrote one equation, and I wanted just the bond enthalpy, I just want the artificial coming in with a pair of scissors, snipping these two things apart, I'm not doing the extra change. In this case here, there would have been an extra delta H in forming the HH bond. So especially on a multiple choice question, make sure sometimes, yeah, we're left with those radicals there, but really just keep in mind the notion, when you bond enthalpy, you're just ripping apart a single bond. So there we go for that. Why do we need to average it over sort of similar compounds? This CH bond actually shows it up in many different molecules. So let's compare this one here, that's just methane. Let's compare it to the fluoromethane molecule. So let's take this very same CH3, but I'm going to have a fluorine attached on the end. I can similarly say, what is the bond enthalpy of a CH bond? Right? I want to know the strength of that bond there. This fluoromethane here would be a similar compound to my original methane. Now, back in chapter 4, we had said fluorine is very, very electronegative. So it's more electronegative than carbon. We had said it develops a polarity. Not enough to start forming hydrogen bonds, but definitely a fairly uneven tug-of-war. What we're going to see in this chapter here is, because fluorine is so electronegative, this end is so partial negative more than this end being partial positive, fluorine has what's called a electron withdrawing effect. It can actually pull some of the electron density from other bonds here towards itself. Remember, the electrons aren't really sort of stuck in these bonds here. They're always bouncing around here. If they notice there's a fluorine on the end, they're going to be withdrew towards the fluorine here. So let's just write that down in words here. Fluorine has electron withdrawing effects. And if you can imagine with me here, well, I am still interested in just the strength between a C and H bond, and yet here, the fluorine is pulling away some of the electron density. It's actually weakening this bond here. The CH bond here in a fluoromethane I would expect to be weaker than a CH bond here. Because I want this as a method to form delta H for any reaction, then I'm going to do what I'm going to just put together a whole bunch of similar compounds. I'm going to figure out, well, sometimes it may be stronger, maybe 416. Sometimes it may be weaker, maybe 412. Well, let me just average the two of them. Let me just give you, well, pretty much in the middle, whenever I see a CH bond, I'd expect it to be about 414. So that's why we refer to it as an average bond enthalpy. I'm going to show you where I get this number here, this 414. So I'm going to just scroll up to the top here just with the data booklet. Let's first look at table number 11. These are talked about here. Bond enthalpies is what we just talked about. This is how much energy is put in to break a bond. So this one here is ripping apart bonds. How this table here is laid out is it separates single bonds on top. So far we looked at the CH single bond. You just basically crisscross on this table here. Doesn't matter which side you do the C or the H, but you just sort of crisscross it here. You say, okay, the single bond of a CH bond is 414 strong, and this one here has already been averaged. This one here has already been, well, sometimes it's weakened, sometimes it's stronger. On average, when you see a CH bond in the gas state, we're going to say roughly 414. And this is true for all single bonds. You can evenly have gone, well, hydrogen on this side and the carbon on this side. You notice that they just double up the value for either. If you do have the odd double bond or triple bond here, you want to look kind of separate from this table here. You're going to want to look on the bottom here between different elements, because every element has a different radii. Just because we know double bonds are always 4 electrons, depending on how close those 4 electrons get to each center, we may actually have a different bond strength. So I want to just make a quick comparison here. Let's take a look at a carbon-carbon single bond. So to match up my table here, carbon-carbon single bond here is 346. The units here they give me are kilojoules per mole. If you line up an Avogadro number of gaseous carbon-carbon bonds, I need 346 input to rip apart this bond. The double bond value here is 614. So C double bond C, that's a 614. Same units. And then we have C triple bond C. This one here is 839. Hopefully no surprise to you here. As you go from single to double to triple, we notice that the bond gets stronger. You need to input more energy to rip it apart. And yet, when I take a look at this here, a double bond is not just 346 times 2. 346 times 2 is 692, right? If I just took this one, if I just multiply by 2, that should give you the strength of a double bond should be 692. And yet, when they do that experimentally, the bond strength is only 614. That actually tells me, yes, having 2 bonds is stronger than 1, but one of these bonds here is stronger and one of these bonds is weaker. Hopefully from chapter 4, you can be able to tell me why that is. Are these 2 bonds the same? In this case here, one of them is a sigma molecular orbital. One of them is along the internuclear axis. The other is a pi bond. It just happens to be parallel overlap. It's sideways. It's not between the centers. The pi bond is weaker than a sigma, although having both of them is stronger than just having one. So we have stronger. We have that case there. They even throw in benzene for us. Benzene was our sort of turtle-like looking molecule. These are called skeletal diagrams. Basically, we have a carbon on every given corner. Benzene is in resonance here. Is the equivalent of 3 double bonds. But if you do that sort of bond order thing here, every carbon has 1, 2, 3, 3 bonds worth. Trying to be split it 2 different ways as a bond order 1.5, and you see that the sort of 1 and a bit bond, that bond order 1.5 is somewhere in between. 507 is somewhere in between the single bond and double bond. So all that's consistent with chapter 4, and that's what we like. Perfect. I'm just going to touch on here, actually let me mention this part first. We'll notice that the table here, the title is actually a little bit strange. It doesn't just say bond enthalpy, breaking up bonds. It also says our average bond enthalpy. So why this notion? One of them is bond enthalpy, one of them is average. You can even refer to this as absolute bond enthalpies. These are the exact numbers. How come these are both bond enthalpies and average? I would say you in general, most of these are average. Most of these, depending on sort of similar looking compounds, sometimes stronger, sometimes weaker, they have already given you some sort of middle value. However, there are some bonds that are actually exact bond enthalpies. For example, if I look up the hydrogen-hydrogen bond, so H going across here with H, hydrogen-hydrogen bond is 436 strong. This one here, I can call this 436 is actually an absolute bond enthalpy, or just bond enthalpy for short. It hasn't been averaged. Can you give me a reason why this one here is the exact bond enthalpy and this one here is not average? Remember, what we wanted to do is we wanted to average over similar looking compounds. When I look at the bond strength of a HH bond, I'm going to try to think about other molecules that also have a HH single bond. Turns out this is the only place I will see a HH single bond. H has an incomplete octet. It always has to be terminal. The HH single bond can't exist anywhere else. So therefore, this is the exact number that I need to rip apart exactly this bond. It hasn't been averaged. So therefore, you can just make a note here. This bond only shows up here. So because I only have one species, I don't actually have other molecules that happen to have this bond here. So therefore, it's an absolute bond enthalpy. They do like asking you that question on tests. So that's the difference. Many bonds will show up in many molecules. I have to average them. If the bond only shows up, like in this case here for a diatomic, these are exact, or these are bond enthalpies. That's why we have both. just for completeness sake here, before we get back to finding delta H, on table number 10, be really careful which table you're looking at. Table number 10 is actually formatted in exactly the same fashion. It talks about single bonds, you sort of crisscross. Well, a carbon and a hydrogen bond here is 108, but this time, instead of looking at the bond strength, the energy needed to rip apart bonds, this time it's just a measure of length. This time it's just a measure of how long that bond is. So when it says 108, you'll notice the units here aren't energy units. It's not kilojoules per mole anymore. This is just times 10 to the negative 12. It's on the order of picometers. This is actually saying how long the bonds are. So if I just match this up this time again, let's go carbon-carbon as a single bond. That's 154. That's going to be 154 picometers. Carbon-carbon double bond on the bottom. So we have 134 picometers. Carbon-carbon triple bond is 120 picometers. It does have something to do with the atomic radii, but they've done for you here. Remember, radii sometimes, it's hard to figure out how far out to measure the orbital to. Let's just figure out if I have two nuclei together, let's just figure out the distance between those two nuclei. And this right here also shouldn't surprise you. As we go from single to double to triple, they even throw in that benzene, that 1.5 here, that's 140 as well. The bonds tend to get shorter. You should be able to explain to me the reason for that here. This is going from 2 electrons to 4 to 6. The more electron rich that electron domain gets, it's going to end up pulling in the two centers in tighter. And as you get closer, the bond themselves gets shorter, and we already said here the bonds themselves also get stronger. So just keep watch of that there. You can't memorize then, oh, a single bond is always 346. This is a single bond between C and C. If I have a single bond between, let's say right below it, we have silicon. So silicon bonded with silicon here, that one there is 226. That one there is actually a weaker bond. So Si and Si, even though valently speaking, they have 4 electrons apiece. I don't know if that's a word. We have 226 here. Again, because silicon here is 1 row lower, the atomic radii is a little bit larger. Even though this bond here is going to be the very same 2 electrons I'm trying to rip apart, it's actually going to be weaker, easier to rip apart. So we're going to take this table here, make sure you have this handy. We're going to use it for a lot of our number crunching for this. We're going to basically do this notion here. Let's compare how much energy in. Let's sort of get a feel of how much energy out. And yet the formula that I'm going to show you here does a little bit of a twist. I'm not going to worry about breaking and necessarily forming. What I'm going to do is I'm going to worry about how much energy to break apart the reactants and how many to break apart products. How many to break apart products is representative of how much is released. We're going to come back in a later lesson to sort of justify this formula here. Again, lots of formulas, lots of definitions in this chapter here. This is now the second way of finding delta H. If you're interested in finding delta H, I'm going to specify this is delta H of any reaction. It doesn't have to be necessarily a bond enthalpy reaction or something like that. So any reaction, it could be decomposition, synthesis, redox, whatever. But if you're deciding to use the bond enthalpy way of doing it, what you're going to do, there's a scary little sigma symbol. The sigma just means add up. We're going to take the bond enthalpies on the reactant side. And what we're going to do is we're going to subtract off the bond enthalpies on the product side. We'll come back to what this not symbol means in a later lesson, but that's generally what we do. What you can think about how this formula works here is this is trying to figure out here the energy used to break the bonds on the reactant side. The reason why I sum up is it's possible that I may have a compound that has many bonds. It's possible I can have multiple, like many different reacting species. I want to add up all the energy I'm putting in to rip apart bonds. You'll notice here I'm comparing it just to bond enthalpies. So this one here is still energy used to break something, but in this case here we're using energy used to break products. For the time being, you can think of that somehow indirectly. That refers to how much energy do I get back out of this reaction. If I compare how much energy to break the left-hand side and how much to break the right-hand side, that should give me an overall energy change for the reaction. So let's try this out here. We're going to start off with just a very simple equation here. H2Cl2 becomes 2HCl. And the question here is find the delta H. Find the enthalpy change. You might not know exactly how much energy we have before or after, but over the course of the reaction and looking at what bonds formed and what bonds broken, you should be able to figure out the overall delta H. This formula here does have to be reactants minus products, even though by the time you find this delta H here is still how does the enthalpy of products minus enthalpy of reactants. So we're always interested in, over the course of the reaction, did I gain energy endothermic? Did I lose energy exothermic? It's just when I use bond enthalpy numbers, this bond enthalpy way of solving it, the formula has to be reactants minus products to make my sign correct. Here, you always need to start off with a Lewis picture because we're interested in bonds here. We need to know what types of bonds we have. So we have a hydrogen-hydrogen bond, we have a chlorine-chlorine bond. Those are absolute bond enthalpies. Those bonds only show up in these exact compounds here. What I'm going to end up forming is I'm going to end up forming HCl. So we know, chemically speaking, what has to happen is this H2 molecule has to run into Cl. They have to collide hard enough that these bonds here have to rip apart. We're going to refer to that there as the bond enthalpy of the reactant site. I'm forcefully coming in. I'm endothermically putting energy in to rip these guys apart. Realistically, what's happening is the electrons are moving. We're ending up creating a new bond between H and Cl. When these bonds form, what's happening here is energy is actually being released. But what the formula says here is it doesn't look at how much energy is released. It tries to measure how much is released by saying, well, what if I came in and also broke apart these bonds? What if I got a gauge on how strong these bonds themselves were as well? If I compare the relative, how much to break these bonds versus how much to break the ones on the product side, I should be able to get an overall, well, did I input more energy or did I get energy back? So there we go. All these are single bonds here. These ones here have to be gases. So that's the limitation of bond enthalpy. In a later lesson, we're going to do a more experimental way here that actually doesn't rely on things being gases. So this is a nice approximation. This is a nice sort of first step. But if I have another way of finding delta H, I generally prefer other ways. So let's have a look at our formula here. I would always write our formula just so that I know which one minus which one. The math in this section here is super simple. So we're going to go bond enthalpy. I just put R for reactants. Subtract out the bond enthalpy for products. Let's make a tally of what are the bonds I'm breaking on the reactant side. On this side here, I'm breaking an HH bond. So let's take a bond enthalpy of H single bond H. And that's sigma. Let's add up the bond enthalpy. The other bond I'm ripping apart is a Cl-Cl single bond. All that's in brackets here. We're going to minus off the bond enthalpy. Again, I want to emphasize here we're comparing the breaking of either side. The relative will give me the delta H overall. So this is going to be the bond enthalpy on the product side here. This is going to be the HCl bond. And yet, if you look at your numbers, sure, every molecule only has one HCl single bond. But in our balanced equation, I actually want to break 2 moles worth of this bond. That's where that pesky little 1 mole actually saves us. Because I know my table always gives me the values for the 1 mole equivalent, if I now need to break twice as many of this bond here, I'm going to multiply this bond enthalpy by 2. So let's just have a look here. Take a look at your table 11. So don't take a look at bond length. Take a look at the bond strength. Double check my numbers here. I was getting 436. Bond enthalpy 242. This one here, twice the bond enthalpy, so twice the value on the table between an HCl single bond. You just crisscross those on the table here. We're doing really simple math here, just simple plus and minus, right? And we end up with a delta H of our whole reaction as negative 184. First, the units are going to be kilojoules per mole because our table tabulates all of these units as kilojoules per mole. If you line up an Avogadro number of this one here, every time you run this statement, we find that the delta H is actually negative. Delta H negative actually means exo. So we've actually done this bond enthalpy method. We managed to find delta H, and we managed to say every time you run this statement, there's a 184 on this side here. You end up releasing off 184. Not only can I tell it's on the product side based on these numbers, I know how much energy is released. Again, this one here implies per mole of reaction. Every time you run this statement, every 1 mole of H2, 184. Every 2 moles of HCl, I get 184. For an exothermic reaction, if you look at this formula, why was this exothermic? How could this formula turn out to be negative? Well, because I'm subtracting 2 numbers, for me to get these as an overall negative number, I can make a general comparison here. Well, I need to go smaller number minus bigger number. The reason why we're exo is either the reactant bonds, generally speaking, reactant bonds are weaker, so they come with smaller bond enthalpies. So that's true in one of these cases here. The Cl-Cl single bond was only 242 strong. The other one was some 431. Or the other implication here is because I'm adding up all the bonds that I'm breaking, maybe there's less bonds that I'm breaking. Bonds are weaker or there's less bonds on the reactant side. So they like asking you that also on a multiple choice. How come this was exo? Is it that the product bonds are stronger, reactant bonds are stronger? That's what they're talking about here. For my overall difference here to be negative, this first side had to be smaller. Let me leave you with one question here. This one here should be a fairly easy way of doing it. Let's find the delta H. And this time what I want to do is I want to do the Haber process. So Haber process is one thing that you should have memorized from chapter 3. It was taking inexpensive nitrogen, about 79–80% of our air, reacting it, synthesizing it with H2, becoming 2NH3. You should be able to tell me the catalyst for that being iron. Again, bond enthalpy is limited here. This one here has to be gaseous, gaseous, gaseous. We're just trying to find the delta H of this reaction using bond enthalpy. Start off with a Lewis diagram. And NN is actually an N triple bond N. And HH is going to be H single bond, and yet there's 3 of them, so I need to multiply the bond enthalpy by 3. How about the NH3 molecule here? NH3 is an ammonia molecule like that, trigonal pyramidal. I'm not worried about the lone pairs and the laced here, but what I'm comparing here is bond enthalpy will only give me the strength per bond. I can look up on the table how strong an NH bond is. You'll notice in this molecule I actually have 1, 2, 3 of these NH3 bonds, and given the balancing number, I'm actually going to rip apart a total of 6 NH bonds. So not only do you do the Lewis to show me what type of bond, make sure you tabulate your numbers. Fortunately for us, the table gives us numbers per mole. I can just scale up the values accordingly. So I'll leave you to finish this one off here. If I want to find the delta H of this reaction here, write out the formula, bond enthalpy reactants minus off bond enthalpy products, add up all the bits on the reactant side and the bits on the product side. This time I'm going to look up what's the average bond enthalpy. That's actually an exact bond enthalpy of N triple bond N. That's the only place that it shows up. I add up 3, the bond enthalpy of HH single bond, and then I'm going to minus off 6 times the bond enthalpy of NH single bond. So have a look at table number 11. Careful you're not looking at table 10, even though it's formatted the same way. Table 11 gives you bond enthalpies. When I did this previous, I believe I got negative 92, 93 or so, right? So we see that it's exo. So 92 kilojoules per mole. And again, in this case here being exo, you can say, oh, for 2 things that are subtracted, give a negative number here, it must mean these guys here were weaker, or it means I had less bonds. While I'm breaking some 6 bonds on the other side, that's why the other term became bigger. So try using table 11 for yourself. Try to verify. It should be about negative 92 or 93, give or take. All right. So if you have any questions, just let me know. Thanks, guys.